Welcome back. In the last few videos, we saw that vanilla RNNs can suffer from several problems such as exploding gradients as well as vanishing gradients. What we will be doing in this video is to look at a few alternate RNN architectures. They are slightly more complicated than the plain architectures that we saw in the last few videos. So, just to recollect what we have done so far, we looked at the plain or vanilla RNN as it is called. It is a very simple idea. You have your input coming from here and you also have a previous layer contributing from here. So, the input layer we call as xt, and there is also an input coming from the previous layer which is ht minus 1, where t is the level at which we are looking, and the output or the input to the next layer is ht and the output here is yt. Now, the formulation we saw was very similar to what we have been seeing, whether it is CNNs or ANNs. It is simply a linear combination. In this case, W and U are matrices, weight matrices. This linear combination followed by a nonlinearity. I had also mentioned that the typical nonlinearity that we use within RNNs is a tanh layer. Now, the output, which is optional, you can take out the output at any point, as we saw in the various combinations of RNNs or various characterizations of RNNs that we saw in the previous videos. So, you have an optional nonlinearity, it might be simply linear or it could have some nonlinearity there, and times yet another weight matrix multiplied by the output at ht. Okay. So, this is typically what is defined as yt. So, this is what we call a vanilla or a plain RNN. As we saw in the previous video, vanilla RNNs have trouble with either vanishing or exploding gradients during backpropagation. Why is that? Because repeated operations of this sort, as we saw in the backpropagation through time video, repeated operations of that sort can actually make the gradients either increase continuously or decrease continuously depending on the eigenvalues of these matrices. So, this makes it hard to calculate deep layers, and all this difficulty goes back to the fact that machines have finite precision. If you did not have finite precision, even a vanishing gradient would not go exactly to 0 and you will learn something. But typically what happens is, if the vanishing gradient becomes very small and smaller than your machine cutoff or machine epsilon, you are not going to learn anything and your learning algorithm is basically stuck when it uses some variation of gradient descent. Similarly, with exploding gradients, it is possible that it might rise really high and then drop, but that will not happen because you will always hit the maximum limit of machine largest numbers, and that will grow up unboundedly. Okay. So, you can have various problems, but in either case, for all sorts of practical algorithms, vanishing as well as exploding gradients is a huge problem, and you are unable to train deep layers. What do we mean by deep layers? Lots and lots of layers. So, typical language tasks can use 50 to 100 layers, and even engineering tasks might require that many, at least a few of them. In such cases, you will find it really impossible to train this, and that was the situation till the 90s. So, vanilla RNNs were not used very popularly for anything other than toy tasks. For an exploding gradient, there is actually a method, as we saw in the previous videos. You can use gradient clipping, that is, you can hit a maximum size of the gradient and make sure that all gradients do not cross this threshold. Okay. But for vanishing gradients, usually there is only one solution, which is to use an alternate architecture. That is, you have to tune this methodology of simply doing g of wht plus uxt minus 1. And the earliest work on this, and still very popular architecture, is something called LSTM, which stands for the humorously named long short term memory. Okay. So, the short term sits together, and I will explain it shortly. So, long short term memory, this is by Hochreiter and a very famous researcher in this field called Professor Schmidhuber. Okay. So, this is in 1997. So, Schmidhuber has worked extensively in this area, and he has worked in many other areas also. He has got phenomenal contributions in the field of machine learning. Okay. Recently there is a slightly simplified version of this called the gated recurrent unit, also called GRU for short, LSTM and GRU for short, and we will look at both these architectures in this video and the coming videos in order to see how is it that they will help the deep layer training part. Now I want to mention that it is recommended that you can look at the original papers. They are a little bit hard to read, especially the LSTM paper is quite hard to read. We will be simplifying both the explanation as well as the expressions that we will show here. In general, when you use RNNs, typically you use either LSTM or GRU. Where you use which is still a matter of art, but we will give a few suggestions in the next few videos. So what is the basic idea? The basic idea with which LSTM and Professor Schmidhuber had started was the idea that human beings don't simply sequentially process something. Okay. So if we say something like Balaji is taking a class, he talked about machine learning. Okay. So this sentence in order for he to work out, you need a long term dependency, as we saw in the previous videos, and this he relates to the person who is speaking, and there is a lot of stuff in the middle. Now how the brain does this is using something called short term memory. Now within the cognitive sciences, as I understand it, there is a lot of research on how many items we can keep, and the general consensus based on a paper a few decades ago is something like 7 items is something that we can keep in our mind in our short term memory. These are sort of our small computational RAM. So if I give you too many items, or if I give you a long phone number or a long number, you can't remember it, but you can remember about 6 or 7 items in a short term space which we can immediately access. So what is also understood is the brain has 2 sorts of mechanisms, or at least we think that there are 2 sorts of mechanisms. There is something called short term memory and long term memory, and the algorithm that we have used here effectively only has a short term memory of 1, which is ht immediately. The immediate value it uses is simply that of xt and ht minus 1, but it does not store sort of the context where ht minus 1 came from. This is a very rough example, or this is a very rough explanation of what happens. So the basic idea here is to either have a separate cell So this is what Schmidhuber did in LSTM, which is to have a separate cell for memory, and GRU also uses some memory like operations. So just to explain, and I will show this mathematically shortly, if you see here ht depends on ht minus 1 and xt, and when I move on to the next unit, ht plus 1 explicitly depends only on ht, and it has completely forgotten ht minus 1. Okay. There is of course some portion of ht minus 1 hidden in ht, but ht plus 1 in general has not using ht minus 1 explicitly. So what GRU and also LSTM do is try to keep some portions of even prior computations stored. Some of you who have done iterative methods might know something like relaxation schemes or successive over relaxation. That also works on a similar principle, as you will see in the formulae that will be shown. So let us come to the idea of GRU. Now in order to explain GRU, we are going to use a slightly different version, which we will call Simplified GRU. This is thanks to Professor Andrew Ng. Just to be clear, this is not a practiced algorithm. Okay. So this is something we are using just in order for explanation. The actual thing in practice is GRU, where I will be showing you. It is a slight modification of the simplified GRU architecture. Okay. So, let us come back to our original vanilla RNN architecture. We had xt, we have ht minus 1, ht comes out. So, we say in general that ht is tan h of w ht minus 1 plus u xt. Okay. So, this is the output of the vanilla RNN. Okay. So, what simplified GRU does is labels this, instead of calling it HT, we will call it G. Okay. So, G is equal to tan h of this term. We are going to label this something else. Well, remember the linear combination was always called Z. So, we will call it ZG, okay, where ZG is equal to W HT minus 1 plus U xt. Remember, W and U are matrices, and for a particular reason, instead of calling them simply W and U, we will call them WG and UG. Okay. So, remember, up until now nothing has changed. This is simply the output of the vanilla RNN. Okay. Okay. So, if this is G, what is HT? So, simplified GRU works in the following way. We will take a linear combination, okay, of the vanilla output and older computation. Okay. So, what does that look like? It looks like this: HT is equal to 1 minus lambda times G plus lambda times HT minus 1. Okay. So, notice this is some scalar for now. I am going to modify this shortly. So, if you see this is simply a linear combination. This is our vanilla output and this is my older output. How does this help? What we are saying is, I will not simply take whatever I have got right now, but I will also retain some portions of whatever computations I did before. Going back to the example that I used here, what we hope is in the HT minus 1 some portion of this term Balaji is stored. Okay. All this is very vague, but much like CNNs, all these algorithms were made with several heuristics. You will see that there will be a separate cell for memory in long short term memory, but I wanted you to get the overall heuristic idea, which is retain some portions of the old computation, also add a new computation. So, when is this a nice linear combination? When lambda belongs to is simply an interpolation, when lambda is a number between 0 and 1. Now, this is not quite simplified GRU. I am going to write the form shortly, but remember what this functions like. You can think of lambda as if it is a valve. Okay. The valve is like this: when the valve is turned to 1, you only retain what was done before. So, HT is simply equal to HT minus 1, it is pure memory. Okay. So, when lambda is equal to 1, you have HT equal to HT minus 1. This is pure and simple memory, no computation at all. Okay. When lambda is 0, then what happens? HT is equal to G, which is you get plain RNN. Okay. So, you can think of simplified GRU effectively as a linear combination of just memorizing and not saying anything. Every word will mean the same thing if we are using a language task, okay, or pure RNN. Okay. So, it is a linear combination, it is sort of an interpolation between a pure memory task and a pure computation task. Okay. So, that is what simplified GRU does. So, let us look at the actual simplified GRU exploration. It is like this: HT is equal to 1 minus F Hadamard product G plus F Hadamard product HT minus 1. Okay. So, this F, just like a valve, this F is called the forget gate. Okay. Okay. Once again, remember, when F is 1, you will purely get memory, and when F is 0, you will get vanilla RNN. Okay. So, now what is the distinction between here and here? There lambda was a scalar, here F is a vector. Okay. Just for the sake of clarity, let us say HT was a 50 cross 1 vector. Let us say G was also a 50 cross 1 vector and HT minus 1 was also 50 cross 1, then in order for the Hadamard product to work, F also has to be 50 cross 1. Now, why would we take F to be a vector? Because it is possible that you might want to remember a few things and forget a few things within a vector, okay, within the H vector. So, what this gives us, independent, I will call them valves for each component of H. Okay. That is all fine, but what value of F do we choose? And here we use the general principle of whatever we have been doing in neural networks, which is we never really specify any component, we let the algorithm choose it. Okay. So, this is introduce parameters to be trained. It is the same as ANN weights, it is the same as CNN kernel weights. Similar to that, we will assume F is full of parameters that ought to be trained. But remember, F also has to be between 0 and 1. Okay. Why is that? Only then does the linear combination work out well, only then does it look like interpolation. Okay. So, if I want F to be between 0 and 1, you remember from logistic regression that we have one function that always squeezes any function into 0 and 1. So, the same principle applies here. So, we will keep F as a sigmoid of something. A sigmoid of what? Same idea, we have linear combination of only two vectors here. At any place, you have these two vectors HT minus 1 and XT, and you make them a linear combination of this. I will keep another W, another U, but I wanted to distinguish it from the W and U I used here, which was WG and UG. So, I will call it WF UF. Okay. So, you will see this theme repeated again and again, and I hope that if and when you are in the position of making an algorithm of your own, you remember that there are very simple things that are going into any sort of neural network. What are the basic ideas that we have seen so far? Linear combination, non-linearity. Okay. So, here is the linear combination, here is the non-linearity. How did we decide on the non-linearity? Because we have some idea of what F should behave like. F should behave like a valve. So, I want it between 0 and 1. So, the non-linearity I will use is sigmoid. Okay. So, let me put it together and hopefully it will become clear then. So, the summary is as follows. I want to say that HT is a linear combination or some sort of linear combination of HT minus 1 and G, where G itself is effectively the output of a vanilla RNN. We decided that G was tan H of WG HT minus 1 plus UG XT. Okay. F was sigmoid of ZF, where ZF is equal to WF HT minus 1 plus UF XT. In order for us to see this symmetrically, I will even erase this and call it tan H of ZG, where ZG is WG HT minus 1 plus UG XT. Okay. So, this is essentially simplified GRU. Okay. Now, it is conventional for us to represent all these new architectures using a figure. I am going to make a figure of my own. This might differ from the ones that are there online or wherever you find in other textbooks, but this is just for a pictorial visualization of what is going on. Some people find it clearer to use this, some people prefer to use simply the formulae that I have written before. Okay. So, let us see this. Okay. So, what we have is, as before, we have HT minus 1 coming from the previous cell, we have XT as the input. Now, the two combine. So, let us take this in. The two combine to give, I will call it G itself. So, if you take tan H of ZG, you get G. Okay. Now, from G, you go a little bit further, there is a valve which is multiplied by 1 minus F. Similarly, HT, there is a valve which is F. Go further, add the two together, and what comes out is HT. Okay. This is the straightforward figure expressing all this here. Remember, even F is simply sigmoid of ZF, where ZF is a linear combination. So, all expressions that you will see within neural networks, I have said this probably 100 times through this course, are simply one linear combination followed by a non-linearity. That is also true for this simplified GRU. Okay. But as I said before, simplified GRU is not the algorithm actually in practice. What is in practice is the usual gated recurrent unit, it is a small variation of what we had in simplified GRU. So, this I will call the full gated recurrent unit. So, the expression for that is very similar to the one that we had before with some small variations. So, this portion is this same f times HT minus 1 plus, instead of 1 minus f times G, which was the vanilla RNN output, this is a modified vanilla RNN output G prime, and I will write the expressions now. G prime is tan h of Zg, f is sigmoid of Zf, okay. Instead of equal to, I will put semicolon, I guess that is more appropriate. Zf is as before Wf times Ht minus 1 plus Uf times Xt. Zg used to be Wg times Ht minus 1 plus Ug times Xt, and now there is a small change to that. There is another valve here, this is called the remember gate, okay, or the remember valve. So, instead of simply having Ht minus 1, you add yet another parameter there, R Ht minus 1 plus Ug times Xt. R also should be between 0 and 1. Now, what do we do about R? It should be trivial by now for you to understand this. It is simply sigmoid of some other thing called Zr, where Zr is equal to Wr Ht minus 1 plus Ur times Xt. Okay. So, this is the full gated recurrent unit. Okay. A few comments here. So, what is it that we have achieved by doing this? First thing, we have introduced many more parameters. Remember, in the usual vanilla RNN, we only had two matrices W and U. Okay. Now, you have 6 sets of matrices Wg, Ug, Wf, Uf and Wr, Ur. So, now you have increased your number of parameters by a factor of 3. Okay. So, we have, and we will see in LSTM that it is a little bit more when you go to LSTM, it is 4 times rather than just 3 times, but for GRU it is 3 times, and if we go back to simplified GRU it was 2 times, okay, Wg, Ug, Wf, Uf. So, the fully gated recurrent unit gives you more parameters to play with, okay. But if it gave you more parameters to play with exactly the same results, then it won't be useful. What happens is, this is works much better for deeper networks. It does not mean that vanishing gradients are no longer going to occur, it is just that you are able to train deeper networks. So, just as a simple example, for certain cases if you were able to do only 10 layers with a normal vanilla RNN, you could go up to maybe 70, 80, 90 layers with fully gated recurrent unit. Okay, so that is the first thing, which is you use up some extra parameters, but you do get better training, okay, you get better training. The second thing is you have a little bit of more non-linearity which is sitting in the system, okay, which tends to mean that you can get and train richer kind of architectures using the full GRU. As of now, for several applications, LSTM is still the first choice. LSTM is something that we will be covering in the next video. It will be a brief video because most of the inputs have already been covered here. So, LSTM is very similar to the full gated recurrent unit. Like I said, it will have 4 times the parameters, but even though it is older, it is still more or less the industry standard. GRU, since it has fewer parameters, is easier to train, but it goes somewhere in between the vanilla RNN and LSTM. Thank you.